Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a question that feels both futuristic and deeply human: the problem with uploading your consciousness. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the question of whether the human mind can truly be copied into a machine. And if your thoughts begin to wander, that's perfectly fine. Let them drift. We'll still be here, quietly unfolding the story. There is something strangely comforting about the idea of uploading consciousness. The promise sounds almost magical. You could preserve yourself, escape aging, outlive your body, perhaps explore distant galaxies as digital light instead of fragile flesh. It is a modern version of an ancient wish to continue. But before we can ask whether we can upload a mind, we must step back and ask something even more basic. Do we understand reality well enough to make such a claim? Because uploading a consciousness is not just a technological challenge. It is a statement about physics. It assumes that the universe is knowable in a certain way. That information can be fully captured. That identity can be preserved. That mind is something we can scan like a photograph. And tonight, we begin at the widest possible scale, not inside the brain, but inside the cosmos itself. If you step outside on a clear night and look up, you might feel that the universe is vast but orderly. The stars trace predictable paths. The planets follow elegant orbits. Physics, it seems, has everything under control, and in many ways it does. But here is the quiet surprise. Everything we can see, stars, planets, galaxies, gas clouds, even black holes, makes up only about 4% of the universe. The remaining 96% is something else. We call it dark matter and dark energy. Those names sound dramatic, but they are really placeholders. They mean quite simply, we do not know what this is. Dark matter appears to hold galaxies together, like invisible scaffolding. Dark energy appears to push the universe apart, accelerating its expansion. Together they dominate the cosmos. And yet we have never directly observed what dark matter is made of. We have never isolated a dark energy particle. In fact, we're not even sure that dark energy is a particle at all. For a long time, scientists modeled dark energy as something called the cosmological constant. That is a number in Einstein's equations that represents a steady, unchanging energy density filling space. Imagine the universe as a loaf of raisin bread rising in the oven. The raisins are galaxies, and the dough between them stretches. The cosmological constant would be like a steady heat source, evenly causing expansion. But recent observations, including large surveys of millions of galaxies, suggest something subtle and intriguing. The expansion may not be behaving exactly as expected. Some data hint that the so-called constant may not be perfectly constant after all. It is too early to be certain. The measurements are delicate, the uncertainties are real, but even the possibility reminds us of something humbling. The largest structure we know, the universe itself, may still contain ingredients we do not understand. There is also a dramatic scenario called the Big Rip. In this idea, dark energy grows stronger over time, eventually overcoming gravity at every scale. Galaxies would drift apart, stars would unbind, planets would loosen from their orbits, even atoms could be torn apart as space itself stretches infinitely. It is a haunting image, but here is the calming part. current evidence does not strongly support this scenario. For the Big Rip to occur, dark energy would need to behave in an extreme way, sometimes called phantom energy, something that violates familiar energy conditions in physics, and so far we have no evidence for such exotic behaviour, so the universe is not likely to rip itself apart tomorrow. Still, the deeper lesson remains. We live in a cosmos where 96% of the driving ingredients are not fully understood. We describe them with equations, we infer them from gravitational effects, we model them with simulations, but we do not hold them in our hands. Now pause for a moment and let that settle. If we do not fully understand the large-scale engine of the universe, how confident should we be when we claim we can fully capture the human mind? Uploading consciousness assumes that the universe is, in principle, completely knowable. That if we measure carefully enough, compute precisely enough, and scan deeply enough, we can reconstruct every relevant detail. But cosmology gently reminds us, reality may be richer than our current maps. This is not an argument against progress. Science has illuminated astonishing truths. We know the age of the universe to within a small margin. We can predict gravitational waves. We can detect planets orbiting distant stars. And yet, the cosmic story is still incomplete. Imagine trying to write a detailed biography of a person while missing most of the pages of the book. You could infer a great deal from the chapters you have. You might even get the broad strokes right. But there would always be a margin of uncertainty. That is our current situation with the universe. And uploading consciousness is not merely a medical or engineering task. It depends on the deepest layers of physical law. It assumes that information is stable, measurable and transferable, without hidden variables lurking beneath. So before we descend into neurons and quantum states, we begin here, under the quiet night sky, acknowledging something both humbling and oddly comforting. We do not yet know everything. The universe is not a fully solved puzzle. It is a landscape still unfolding, and perhaps that is a good place to begin. When we look at the universe on its larger scales, galaxies swirling like luminous islands, clusters drifting through cosmic space, one theory guides our understanding with remarkable precision. That theory is called general relativity. It was introduced by Albert Einstein over a century ago, and it describes gravity not as a force pulling objects together, but as a bending of space and time themselves. You can imagine space as a vast flexible fabric. Place a heavy bowling ball on a trampoline and the surface curves. Roll a marble nearby and it spirals inward, not because the bowling ball is pulling it directly, but because the surface beneath it has changed shape. That bending is gravity. General relativity works beautifully at large scales. It predicts the motion of planets. It explains black holes. It anticipated gravitational waves, ripples in space and time, which we have now detected. When it comes to the grand architecture of the cosmos, this theory performs like a master architect. But when we shrink our attention down to the tiniest scales, atoms, electrons, particles that flicker into and out of existence, another theory takes over. That theory is quantum mechanics. Quantum mechanics does not describe smooth curves in space. Instead, it describes probabilities, uncertainties, and strange behaviours that defy our everyday intuition. Particles can behave like waves. Waves can behave like particles. Two particles separated by enormous distances can share a connection that seems instantaneous, though it does not allow information to travel faster than light. If general relativity is the graceful geometry of the cosmos, quantum mechanics is the restless shimmer beneath it. Here is the quiet tension. These two theories are both extraordinarily successful. Each has been tested again and again. Each makes predictions that match observation with astonishing accuracy, and yet they do not fit together into a single, unified description of reality. It is as though we have two maps of the same country. One map is excellent for highways and mountain ranges, the other is perfect for city streets and alleyways. But when we try to overlay them, the borders do not align perfectly. The scales differ, the coordinates drift. Physicists have spent decades attempting to reconcile them. There are elegant mathematical proposals. String theory suggests that particles are tiny vibrating strands existing in additional spatial dimensions. Loop quantum gravity proposes that space itself may be woven from discrete loops at unimaginably small scales. These frameworks are mathematically rich and deeply imaginative, but so far there has been no experimental confirmation that either provides the final answer. Now, you might gently ask, what does this have to do with uploading consciousness? The connection is subtle but profound. The human brain is not only a biological system, it is also a physical system. Every neuron obeys the laws of physics. Every electrical signal, every chemical exchange, every flicker of activity is ultimately grounded in the same reality that governs galaxies and quarks. If our most fundamental physical theories are not yet unified, then our understanding of matter itself remains incomplete. Imagine attempting to copy an intricate mechanical watch while still debating how the gears fundamentally interact at the smallest scale. You might replicate the visible parts, but if there were hidden layers beneath your understanding, your copy might miss something essential. There's another delicate point. Light plays a central role in both major theories. In quantum mechanics, light behaves as packets called photons, quanta of energy that can be described probabilistically. In general relativity, light follows the curvature of space and time. It's affected by gravity, bending as it passes near massive objects. Light is sometimes described as the place where the two theories almost meet. It is the thread that runs through both descriptions of reality. And yet, even here, we do not have a complete merging of the frameworks. They touch, in a sense, but they do not fully overlap. This matters because copying a mind requires more than copying structure. It requires copying physical states, and those states are ultimately described by the same laws that govern everything else. If the universe at its deepest level has features we do not yet fully grasp, if there are aspects of space, time, or matter that elude a unified description, then our confidence in perfectly reproducing a physical system as complex as a human brain should be tempered with humility. At this point, it's important not to exaggerate. The brain operates at scales where classical physics, the physics of everyday objects, often provides a remarkably good approximation. Neurons are large compared to subatomic particles. Electrical signals in the brain can be described using well-tested equations of electromagnetism, but often is not the same as always. The absence of a unified theory does not mean uploading consciousness is impossible. It simply means that the foundation beneath our understanding of matter is still evolving, and when we make claims about perfectly capturing and replicating a mind, we are leaning on that foundation. There is also a philosophical echo here. General relativity shows us that space and time are not fixed backdrops. They are dynamic, flexible, responsive. Quantum mechanics shows us that uncertainty is not merely a limitation of our instruments. It is woven into the fabric of reality itself. Taken together, these theories suggest that reality is subtler than our everyday intuition. It is not a simple clockwork machine where every gear can be frozen and duplicated without consequence. So when someone says, "We will scan every neuron and upload the mind," it sounds straightforward. It sounds like making a digital copy of a document. But the universe is not a flat document. It is layered, curved, and probabilistic. And if we are still learning how those layers fit together, then perhaps the story of consciousness must be told with similar care. As we continue, we'll move closer to the microscopic world, into the strange territory where particles refuse to behave like solid beads, and where copying becomes more complicated than pressing a button. The calm night sky may look stable above us, but beneath it, at scales too small to see, reality hums with quiet uncertainty. And that hum may matter more than we realise. If you ask someone what time is, they might say it is what clocks measure. A simple answer, practical, comforting. Time ticks forward. Morning becomes afternoon. Afternoon becomes evening. Causes come first. Effects follow after. But when physics peers more closely at time, things grow quieter and stranger. In Einstein's theory of relativity, time is not a universal metronome ticking the same for everyone. Instead, time stretches and compresses depending on motion and gravity. A clock moving very fast will tick more slowly than a clock at rest. A clock deep in a gravitational field will tick more slowly than one far away from massive objects. These effects are not science fiction. They're measured. Satellites in orbit must correct for them, or our navigation systems would drift. This leads to an intriguing perspective sometimes called the block universe. In this view, the universe is not unfolding moment by moment like a river flowing forward. Instead, all moments, past, present and future, exist together in a four-dimensional structure. Imagine a vast landscape made not only of space, but of time as well. Every event that has happened and every event that will happen is part of that landscape. You're not moving through time in the way a boat moves down a stream. Instead, your conscious experience might be something like a spotlight moving across an already existing terrain. It is a powerful image, a quiet one. But it is important to pause here and breathe. The block universe is a mathematical interpretation of relativity. It arises naturally from the equations, yet it remains an interpretation. We do not have an experiment that proves the future already exists in the same sense as the past. Physics allows the model. Reality has not confirmed it beyond doubt. There is also a related idea called retrocausality. This is the suggestion that future events might influence past ones, not just the other way around. Certain quantum experiments can be described in ways that make this interpretation mathematically consistent. In these scenarios, it can appear as though a measurement made later affects the state of a particle earlier. But here again, we must be careful. These interpretations do not allow information to travel backward in time in any practical sense. They do not let us send messages to our younger selves. They do not overturn causality in the everyday world. They are ways of organizing mathematical descriptions of quantum behavior. There have been proposals suggesting that if faster-than-light communication were ever possible, it might test some of these deeper structures of time, but so far no experiment has demonstrated the transmission of usable information faster than light. Quantum entanglement, which we'll soon explore more closely, creates correlations that appear instantaneous, but they do not allow controllable signals to outrun light. In other words, our equations sometimes whisper possibilities, our experiments remain cautious. Why does this matter for uploading consciousness? Because many bold claims about digital immortality quietly assume a certain model of time and identity. If the block universe was strictly true in a literal sense, then every moment of your life would already exist. In that case, what would it mean to continue digitally? Would you be extending yourself into the future, or simply accessing another part of the landscape that is already there? If retrocausality played a significant role in brain processes, then copying a brain at one instant might not capture the full story of how that brain relates to its temporal context. The brain would not be merely a machine operating in a forward-only chain of cause and effect. it might be entangled in a deeper structure of time itself. Now, to be clear, there is no experimental evidence that human consciousness depends on retrocausal influences. There is no confirmed evidence that the block universe interpretation is physically mandatory rather than philosophically convenient. These ideas remain in the realm of careful speculation, and that distinction is essential. In science, mathematical elegance does not automatically equal physical truth. A model may be internally consistent, beautifully symmetrical, and still incomplete. We have seen this before. The cosmological constant was once introduced by Einstein for aesthetic reasons, later abandoned and then revived when cosmic expansion was observed. Physics evolves, interpretations shift. So when we discuss consciousness and uploading, we must be attentive to the difference between what is experimentally grounded and what is theoretically possible. There is a temptation, especially when discussing the future of technology, to weave together the most dramatic possibilities from every corner of physics. Quantum weirdness, flexible time, hidden dimensions, digital minds. It makes for compelling headlines. But the calm, steady truth is this: we do not yet have evidence that time behaves in a way that guarantees or forbids digital immortality. We do not have confirmation that consciousness is embedded in a retrocausal network. We do not know whether the block universe is literal or metaphorical, and that uncertainty is not a weakness. It is a reminder of where we stand. Imagine holding a partially completed puzzle. You can see sections of sky and ocean clearly. The edges are forming, but large regions in the center remain blank. You can guess the missing shapes. You can propose patterns. But until the pieces are placed, the full picture remains open. Time itself may be one of those missing regions. As we continue inward, from the vastness of cosmic structure to the microscopic rules of matter, we carry this lesson with us. Physics provides extraordinary insight, yet it also teaches restraint. Before we declare that a mind can be perfectly scanned and uploaded into silicon, we must ask, what is the structure of reality in which that mind exists? How does time shape identity? And how much of that structure do we truly understand? The river of experience feels smooth as it flows through our days, but beneath its surface, the landscape of time may be more intricate than we imagine, and that intricacy deserves patience. When we think about copying something, it feels effortless. You copy a file on your computer, you duplicate a photograph, you back up your phone. The original remains untouched, and a perfect twin appears elsewhere. In the digital world, copying seems almost trivial. It feels like pressing a button. But the universe has a quiet rule that complicates this picture. At the smallest scales of reality, there are states of matter that cannot be perfectly copied. Not because we lack better machines, not because we need sharper scanners, but because the laws of physics themselves forbid it. This rule is often called the no-cloning principle. The name sounds technical, but the idea is surprisingly simple. If you have a completely unknown quantum state, something like the exact configuration of a tiny particle at the most detailed level, you cannot make an exact duplicate of it without already knowing precisely what that state is, and even attempting to measure it changes it. To understand this gently, imagine holding a snowflake in your hand. Each snowflake has an intricate pattern. Now imagine you're not allowed to look at it directly. You can only learn about it by touching it. But the moment you touch it, it begins to melt. By the time you finish examining it, the original structure has shifted. That is closer to how quantum systems behave. In classical physics, the physics of everyday objects, if you want to copy something, you simply observe it carefully and reproduce it. If you want to copy a book, you read every page and rewrite it. The book does not change while you're reading it. But in quantum physics, the act of observing is not passive, it is active. Measuring a quantum system forces it into a definite state. Before measurement, the system may exist in a delicate blend of possibilities. After measurement, it settles into one outcome. This blending of possibilities is often described using the word superposition. You do not need to picture equations or symbols. Instead, imagine a spinning coin in the air. While it spins, it is not purely heads or tails, it is in motion, in between. Only when it lands do we see one clear face. Quantum systems are similar, except their spinning is not just ignorance about the result. It is a real physical state of multiple possibilities coexisting. Now here is the crucial part. If you try to copy that spinning coin while it is still in the air, if you try to capture the full richness of its in-between state, you cannot simply duplicate it. The only way to learn its exact condition is to let it land. And once it lands, the delicate in-between condition is gone. In more precise language, quantum information cannot be cloned unless it is already known in full detail. But unknown quantum states cannot be fully known without disturbing them. It is a circle that closes on itself. This principle has been tested experimentally. It is not speculative philosophy. It is embedded in the structure of quantum theory. It ensures the security of quantum encryption systems. It shapes how quantum computers must be designed, and this is where the uploading question quietly reappears. If consciousness depends in any essential way on quantum states, if some aspect of thought or awareness relies on these delicate in-between conditions, then copying a mind may not be as simple as scanning and duplicating data, because you cannot copy what you cannot fully know. Now, it is important to remain balanced here. Most neuroscientists believe that the brain operates largely at scales where classical physics provides a good description. Neurons are not individual electrons, they're large, warm, biological structures. Electrical signals in the brain involve trillions upon trillions of particles acting collectively. At that scale, many quantum effects average out. But many is not the same as all. If even a small but crucial part of consciousness depends on quantum-level states, then the no-cloning rule becomes relevant. Imagine trying to recreate a symphony by copying every instrument, but missing a faint resonance that ties the whole performance together. If that resonance is essential, your copy may sound identical on paper, yet lack something subtle in experience. There is another gentle implication of the no-cloning principle. In the digital world, copying does not destroy the original. But in quantum mechanics, if you attempt to extract full information from a system, you alter it. There is no way to read out all the details of an unknown quantum state and leave it untouched. The act of reading reshapes what is read. So even the idea of scanning a brain at the deepest level must contend with this. A perfect scan would require perfect knowledge. Perfect knowledge at the quantum scale may be physically inaccessible, not technologically inaccessible, fundamentally inaccessible. This does not mean uploading consciousness is impossible. It means that if consciousness rests entirely on classical processes, large-scale electrical and chemical interactions, then the no-cloning principle might not block it. But if consciousness has even a thread woven from quantum uncertainty, that thread cannot simply be photocopied. The deeper lesson here is not about pessimism, it is about the structure of reality. We are used to thinking that information is like text on a page, copyable, transferable, independent of its medium. But quantum physics suggests that some forms of information are inseparable from the physical system that carries them. They are not just descriptions, they are states, and states cannot always be duplicated. As we continue, we will explore another related limit, a quiet principle that tells us not only that copying may be restricted, but that even knowing everything about a system may be beyond reach. The universe, it seems, guards some of its details carefully. There is another quiet rule in the universe, one that feels almost poetic. It tells us that there are pairs of properties we cannot know perfectly at the same time, not because our instruments are crude, not because we lack patience, but because nature itself does not allow it. This rule is known as the uncertainty principle. It was first described by Werner Heisenberg in the early 20th century. And although the mathematics behind it can be intricate, the idea can be felt in something much simpler. Imagine trying to photograph a tiny firefly in complete darkness. To see it clearly, you must shine a light on it. But the brighter the light, the more you disturb its delicate flight. The act of observing changes what you observe. In the quantum world, something similar happens. Take a particle, such as an electron. It has properties like position, where it is, and momentum, how it is moving. The uncertainty principle tells us that the more precisely we know the position, the less precisely we can know the momentum. And the more precisely we know the momentum, the less precisely we can know the position. It is not that the particle secretly has both values, and we are simply failing to measure them accurately. The uncertainty is built into the structure of reality. The particle does not carry perfectly sharp values for both at once. If you prefer a softer image, think of trying to track a small boat in fog. If you focus on pinpointing exactly where it is right now, you lose clarity about how fast and in what direction it is moving. If you focus on measuring its speed and direction precisely, its exact position becomes blurry. The fog is not in your eyes, it is part of the landscape. This principle has been tested repeatedly in laboratories. It is woven into the equations that successfully predict atomic spectra, chemical reactions, and the behavior of semiconductors. Without it, modern electronics would not function. Now, let us bring this gently back to the brain. If consciousness is entirely classical, if it depends only on large-scale electrical signals and chemical concentrations, then perhaps uncertainty at the quantum level averages out. The brain, in that case, might behave like a complex but ultimately classical machine. But if some aspect of consciousness depends on fine-grained quantum states, then uncertainty imposes a limit. To perfectly upload a mind, one would need perfect knowledge of its relevant physical state at a given moment. Every neuron's firing pattern, every synaptic strength, every electrical potential, difference, every molecular configuration that matters, and if, at the deepest layer, those configurations involve properties that cannot be known simultaneously with arbitrary precision, then the idea of a perfectly faithful capture becomes more complicated. This is not the same as saying uploading is impossible. It is saying that there may be a built-in blur at the smallest scales. Consider how we normally think about scanning something. When you scan a document, you imagine capturing every pixel. The scanner reads the page, records the pattern of ink, and produces a digital image. The page does not change because of the scan. The information is passively recorded. But at the quantum scale, scanning is not passive. It is an interaction. An interaction modifies the system. There is an additional subtlety. Uncertainty is not only about position and motion. Similar relationships exist for other pairs of properties. Energy and time are linked in a comparable way. The shorter the time interval you examine, the more uncertainty appears in energy measurements. This does not mean energy conservation fails. It means that at extremely short timescales, fluctuations are intrinsic to the system. If you imagine trying to freeze a brain at an exact instant, capturing every energetic detail down to the smallest component, you run into a philosophical tension. There may not be a single, perfectly defined microscopic state waiting to be copied in the classical sense. There may be a range of possibilities that only become definite through interaction. And here is something even more interesting. The uncertainty principle does not arise because our measuring devices are imperfect. It arises from the wave-like nature of matter itself. At very small scales, particles behave not just like tiny solid beads, but like ripples. And waves have an inherent spread. You cannot compress a wave into an infinitely sharp spike without changing its character. So when we talk about copying a quantum state, we're not talking about duplicating a rigid object. We're talking about reproducing a delicate wave pattern that cannot be fully pinned down in all aspects at once. Now, it is essential to keep perspective. The brain is warm, it is wet, it is noisy. Billions of neurons operate together. Most neuroscientists argue that at this scale, quantum uncertainty becomes negligible in shaping everyday cognition. The brain's behavior, in their view, can be described adequately by classical electrical and chemical interactions. But the uploading claim is not modest. It is not merely about approximating behavior. It is about perfectly preserving identity, preserving experience, preserving the continuity of self. And perfection invites scrutiny. If there is even a tiny layer of irreducible uncertainty at the foundation of the physical processes that generate consciousness, then the dream of flawless duplication faces a subtle but profound constraint. You might still build a copy that behaves identically. It might answer questions the same way. It might recall memories. It might insist that it is you. But whether it captures the full, original physical state, down to the last flicker of possibility, becomes a deeper question. Uncertainty does not shout, it whispers. It reminds us that the universe is not a perfectly crisp blueprint waiting to be photographed. It is more like a living tapestry whose threads shift gently as we touch them. As we move forward, we will explore another factor that complicates the picture. One that suggests that even if quantum effects exist, they may fade rapidly in biological systems, dissolving into the warm noise of life. But for now, it is enough to rest with this idea. There are limits not only to what we can build, but to what can be known. And uploading a mind, if it is ever possible, must pass through those limits. Up to this point, we have been walking carefully along the edge of quantum strangeness. We've seen that some things cannot be perfectly copied. We have seen that measuring at the smallest scales changes what is measured. It might begin to feel as though the quantum world stands like a firm wall in front of any attempt to upload a mind. But now we must slow down, because there is another side to this story. Quantum effects are delicate, they are subtle. They require very special conditions to remain stable. In laboratories, scientists who work with quantum systems often cool them to temperatures close to absolute zero. They isolate them from vibrations. They shield them from stray electromagnetic noise. They build elaborate environments designed to protect fragile quantum states from disturbance. And the reason they go to such lengths is simple. Quantum coherence, the ability of a system to maintain its delicate superposition of possibilities, tends to decay rapidly in warm, messy surroundings. This process is called decoherence. You can think of coherence as a soap bubble floating in still air. Under quiet conditions, the bubble can drift gently, shimmering with delicate colour. But place that same bubble in the middle of a hurricane, and it will not survive long. The human brain is not a quiet laboratory. It is warm, it is wet, it is constantly bathed in electrical and chemical activity. Billions of neurons fire, molecules collide, ions flow across membranes. The temperature hovers around what feels comfortable for life, but would be chaotic for maintaining fragile quantum states. In such an environment, many physicists argue that quantum coherence would dissolve almost instantly. Any delicate superpositions at microscopic scales would be scrambled by interactions with surrounding particles. What remains at the level of neurons and networks would be effectively classical behaviour. This is one reason most neuroscientists treat the brain as a classical system. Electrical impulses travel along axons, neurotransmitters cross, synapses, membrane potentials rise and fall. These processes can be described using well-tested equations of chemistry and electromagnetism without invoking sustained quantum coherence. From this perspective, the brain is not a quantum computer. It is an extraordinarily complex biological machine, but one that operates in a regime where quantum effects average out. And if that is true, then the no-cloning principle and quantum uncertainty, while fundamental, may not block uploading in practice. If consciousness depends only on classical patterns, on large-scale arrangements of electrical and chemical activity, then in principle, those patterns could be measured and reproduced with sufficient precision. But the story does not end there. A small group of researchers have proposed a different possibility. Among them is Roger Penrose, who suggested that human consciousness might involve non-computable processes rooted in quantum gravity. Alongside anesthesiologist Stuart Hameroff, he proposed a model often called orchestrated objective reduction, or simply ORCHOR. The idea, described gently, is that structures inside neurons called microtubules might support quantum coherence long enough to influence brain function. Microtubules are part of the cell's internal scaffolding. They help maintain shape and transport materials. The proposal suggests that within these tiny cylindrical structures, quantum processes could play a role in conscious experience. It is an intriguing idea. It attempts to bridge the gap between quantum physics and subjective awareness. It offers a way for consciousness to be more than just classical computation. However, and this is important, the ORCHOR hypothesis remains controversial. Many physicists argue that decoherence would destroy any meaningful quantum coherence inside microtubules almost instantly. Experimental evidence supporting sustained quantum processes in the brain at the level required for consciousness has not yet been demonstrated conclusively. The debate is ongoing, it is thoughtful, it is not settled, and this uncertainty has a curious effect on our question. If the brain is entirely classical, then uploading consciousness becomes a matter of engineering and scale. It may be staggeringly difficult, but not physically forbidden by quantum rules. If, on the other hand, consciousness depends on fragile quantum coherence that cannot be sustained outside biological tissue, then uploading may face a deeper obstacle. But here, caution is essential. We must not leap from quantum is mysterious to consciousness must be quantum. Nor should we leap from the brain is warm to quantum plays no role whatsoever. Science rarely rewards extreme certainty in either direction. Instead, we find ourselves in a space of layered possibility. At large scales, the brain behaves in ways that appear classical. Networks of neurons fire in patterns that can be measured. Brain imaging reveals rhythms and waves that correlate with attention, sleep, and memory. These observations do not require exotic physics. At very small scales, quantum mechanics governs the behavior of individual particles. Chemical bonds, ion channels, and molecular interactions are ultimately quantum in nature. But whether those quantum features survive long enough, and in organized enough form, to shape conscious experience remains an open question. For our purposes, the lesson is subtle. Quantum mechanics sets limits on copying and knowing. Decoherence suggests those limits may fade at the scale of everyday brain activity. The ORCHOR proposal reopens the possibility that quantum processes might matter after all. Uploading consciousness sits right at the intersection of these uncertainties. Before we can confidently declare that a mind is simply information waiting to be transferred, we must ask whether that information is purely classical, or whether it includes elements that resist stable duplication outside the living brain. The hurricane may dissolve soap bubbles, or perhaps hidden within its swirling winds there are patterns that last longer than we expect. For now, we remain careful. The brain might be classical. It might contain subtle quantum threads. The evidence is not decisive, and so the uploading question remains suspended between possibility and limit, resting on physics that we are still learning to fully understand. Up to this point, we have been asking whether the universe allows perfect copying at the smallest scales. Now we shift slightly. Even if the brain turns out to behave in a mostly classical way, even if quantum coherence dissolves in the warm noise of biology, there remains another quiet constraint. Information is not abstract, it is physical. When you delete a file on your computer, it feels like something purely digital has happened. A few keystrokes and the file disappears. But underneath that simple action, physical processes occur. Transistors switch states. Tiny flows of charge move. Heat is generated. Energy is dissipated into the surrounding air. There is a principle in physics that captures this relationship. It is often called the Landauer principle. In gentle terms, it states that whenever a single bit of information is erased, when a system is forced from two possible states into one definite state, a minimum amount of energy must be released as heat. You do not need the exact number. What matters is the idea. Information processing is tied to thermodynamics. It is tied to energy. It is tied to heat. The universe does not allow information to be manipulated for free. Now, let us return to the uploading dream. To upload a mind, we would need to measure and encode the state of a human brain in extraordinary detail. A human brain contains on the order of tens of billions of neurons. Each neuron connects to thousands of others. Altogether, there are hundreds of trillions of synaptic connections, points, where signals pass from one cell to another. It is a number so large that it resists intuition. Imagine standing on a vast beach and scooping up a handful of sand. Now imagine counting every grain in your hand. Then imagine that the number of connections in your brain is comparable to counting grains across an entire coastline stretching for miles. And those connections are not static. They change. Synaptic strengths shift as you learn. Electrical potentials fluctuate in milliseconds. Neurotransmitters are released and reabsorbed. Proteins move within cells. Ion concentrations rise and fall. Uploading consciousness is not simply copying a frozen wiring diagram. It would require capturing a dynamic pattern, an intricate dance of electrical and chemical states at a specific moment in time. All of that information must be stored somewhere, processed somewhere, maintained somewhere, and each bit stored, each calculation performed, carries a physical cost. Now consider scale. Modern data centers already consume vast amounts of electricity. They require cooling systems to prevent overheating. And yet the amount of information stored in a typical data center, impressive as it is, may still fall short of the full detailed state of a living brain at cellular resolution. To emulate a brain faithfully, one might need computational resources beyond today's most powerful supercomputers, not just in raw storage, but in speed. The brain operates in real time. Signals propagate in milliseconds. If an upload is meant to function as a conscious agent, it must update and process information at similar speeds. And speed also has thermodynamic implications. Faster computation generally means more energy usage and more heat. There is a quiet irony here. Many imagine digital minds as ethereal, weightless, free from the burdens of biology. But the servers that would host such minds would not float in abstraction. They would sit in buildings, they would draw electricity, they would radiate heat. They would obey the same physical laws as any other machine. Information may feel intangible, but it always has a physical substrate. Some theorists argue that advanced computing technologies, perhaps quantum computers, perhaps radically efficient architectures, could reduce energy costs dramatically. That may be true. Technology evolves, efficiency improves. But thermodynamics sets fundamental boundaries. There is always a minimum cost to irreversible operations. There is always a trade-off between precision, speed, and energy. Even if we imagine a future civilization with near-limitless power from stars or advanced reactors, the act of simulating a full human brain at molecular resolution would not be trivial. It would require immense coordination and infrastructure. Now pause for a moment and consider what this implies. Uploading consciousness is often presented as a matter of scanning and copying, but it is also a matter of sustaining a vast physical system capable of running that copy indefinitely. If the upload is to experience continuity, the system must remain stable. It must avoid catastrophic failure. It must maintain hardware, cooling, energy supply. In a sense, the digital mind trades biological fragility for technological fragility. There is another subtle point. If consciousness depends not only on the structural connections in the brain, but also on subtle biochemical states, protein configurations, epigenetic markers, transient molecular gradients, then the informational load increases even further. Each additional layer of detail multiplies the storage and processing requirements. One might respond, perhaps we do not need that level of detail. Perhaps a simplified model would suffice, and that may be so. But the original claim of uploading consciousness is not about approximation. It's about preserving the self, preserving memory, preserving subjective experience, and preservation invites precision. The deeper we look, the more we see that information is not just lines of code. It is a pattern embodied in matter and energy. To copy it perfectly is to recreate that pattern in another physical form, with all its associated costs. This does not make uploading impossible. It does make it heavier in energy, heavier in infrastructure, heavier in physical commitment. The dream of digital immortality is often painted as a liberation from the constraints of flesh. Yet even in silicon, the laws of physics remain. Before we move inward to ask what consciousness truly is, it is worth resting with this quiet realization. Information is not free. It is not abstract. It is woven into the physical fabric of the universe. And any attempt to move a mind from one substrate to another must respect that fabric. Before we attempt to copy a mind, before we debate whether physics allows it, before we calculate energy costs or scanning resolutions, we must pause and ask a deceptively simple question. What exactly are we trying to copy? Consciousness is a word we use every day. We say someone is conscious or unconscious. We speak of conscious thought, conscious decisions, conscious awareness. Yet when scientists attempt to define it precisely, agreement dissolves. There is no single, universally accepted scientific definition of consciousness. Some researchers define it as subjective experience, the feeling of being, the redness of red, the ache of a memory, the quiet presence of awareness behind your thoughts right now. Others define it more functionally. They describe consciousness as the brain's ability to integrate information, to report internal states, to respond flexibly to the environment. In this view, consciousness is about what a system does, and here the distinction becomes important. Is consciousness the experience itself, or is it the behavior that accompanies it? Imagine a perfect mirror. It reflects every detail of your face. It captures your expression, your movement, your posture. But the mirror does not feel what you feel. It doesn't experience the reflection. It simply reproduces the pattern of light. Now imagine a machine that perfectly replicates your speech, your memories, your gestures, your preferences. It laughs when you would laugh. It answers questions the way you would answer them. It claims to feel what you feel. Is that machine a mirror? Or is it a continuation of you? Different philosophical positions give different answers. One influential approach in contemporary science is sometimes called integrated information theory. In gentle terms, it proposes that consciousness corresponds to the degree to which information is integrated within a system. The more unified and irreducible the internal informational structure, the higher the level of consciousness. You do not need to imagine symbols or equations. Instead, picture a network of lights. If each light flickers independently, there is little integration. But if patterns of light influence each other in complex, unified ways, forming a single cohesive pattern, then integration increases. According to this view, consciousness is not tied to specific biological material. It is tied to the structure of causal interactions within a system. If a machine had the same integrated informational structure as a human brain, it might, in principle, generate consciousness. This perspective leans toward what philosophers call functionalism. The idea is that what matters is not what something is made of, but how it functions. Just as a melody can be played on a piano or a violin, consciousness might arise in biological neurons or silicon circuits, as long as the functional organization is preserved. But there is another view. Some thinkers argue that biological material matters deeply. They suggest that consciousness is not merely computation. It is not simply the arrangement of information. It is something that arises specifically from living processes, from the chemical and biological nature of neural tissue. This position is sometimes called biological naturalism. In this view, simulating the brain on a computer would be like simulating digestion. You could model every chemical reaction on a screen, but the simulation would not digest food. It would only represent digestion. Similarly, a simulation of neural activity might represent consciousness without instantiating it. The tension between these perspectives sits quietly at the heart of the uploading debate. If functionalism is correct, then copying the functional organization of the brain might be sufficient. The material substrate, carbon or silicon, would not matter. If biological naturalism is correct, then replacing neurons with circuits might preserve behavior but not experience. And here we encounter another subtle distinction. Behavior is observable. Experience is private. A machine could behave exactly like you. It could insist that it feels joy, fear, curiosity. It could pass every external test for intelligence and self-awareness. Yet we would still face the same philosophical question. Does it truly experience anything, or does it merely simulate experience? This is sometimes illustrated through thought experiments. Imagine a room filled with rule books written in a language you do not understand. You receive messages in that language. By following the rule books mechanically, you produce appropriate responses. To an outside observer, it appears that you understand the language, but internally you are only manipulating symbols without comprehension. The question is whether consciousness is like genuine understanding, or like symbol manipulation that merely appears meaningful from the outside. For uploading, this question is not abstract. If consciousness is identical to certain patterns of information processing, then replicating those patterns might replicate consciousness. If consciousness depends on something more, something tied to biology or to specific physical properties, then replication of structure alone may not suffice. And we must remember, we have not yet resolved this debate. Neuroscience can correlate brain activity with reported experience. It can identify neural signatures associated with wakefulness, sleep, anesthesia. But correlation is not explanation. We can see which brain regions light up when someone feels pain, but we do not yet understand why those physical processes produce the feeling of pain. That gap between physical process and subjective experience is sometimes called the hard problem of consciousness. It is a reminder that even before asking whether we can upload a mind, we are still grappling with what a mind truly is. Perhaps consciousness is entirely physical, reducible to patterns of neural firing. Perhaps it emerges from complexity in ways we do not yet fully grasp. Perhaps it requires certain biological features that cannot be easily transferred. For now we rest with uncertainty. Uploading assumes we know what to preserve, but if consciousness itself remains undefined, then the target of our copying is not yet fully specified. Before building a bridge to digital immortality, we must first understand the landscape we're trying to cross. As we sit quietly with the question of what consciousness is, another possibility begins to shimmer at the edge of thought. What if consciousness is not merely complex computation? What if it reaches down into the quantum fabric of reality itself? This idea is often associated with mathematician and physicist Roger Penrose. Penrose has argued that human understanding, particularly mathematical insight, cannot be fully captured by algorithmic computation alone. In his view, there may be aspects of human thought that go beyond what a purely digital machine could replicate. From this perspective, consciousness might involve physical processes that are not just classical electrical signals in neurons, but subtle, quantum events. Together with anesthesiologist Stuart Hameroff, Penrose proposed that tiny structures inside neurons called microtubules could play a role in this deeper process. Microtubules are cylindrical components of the cell's internal framework. They help maintain shape, transport molecules, and support cellular organization. The proposal suggests that within these microtubules, quantum coherence might persist long enough to influence neural activity in a meaningful way. The idea is sometimes described as orchestrated objective reduction, though the name is less important than the core suggestion that conscious experience may arise from quantum-level events that are sensitive to the geometry of space and time. Now, pause and breathe. This is a fascinating proposal, but it is also controversial. Most physicists remain skeptical that quantum coherence could survive long enough in the warm, wet environment of the brain to play a central role in cognition. As we discussed earlier, decoherence tends to disrupt delicate quantum states rapidly in noisy environments. To sustain meaningful quantum coherence, systems usually need isolation and extremely low temperatures. The brain provides neither. It is a biological storm of thermal motion and chemical interaction. Supporters of the quantum consciousness hypothesis argue that microtubules might shield quantum processes in ways not yet fully understood. Critics respond that current evidence does not support coherence at the timescales required for thought. At present, there is no decisive experimental confirmation that consciousness depends on quantum computation inside neurons. The hypothesis remains open, intriguing, and debated. So why does this matter for uploading? Because if consciousness truly depends on quantum states, if subjective experience arises from delicate superpositions or non-classical processes, then digitization faces a fundamental obstacle. A classical computer processes bits. Bits are simple units of information that can be in one of two states, 0 or 1. Quantum systems, by contrast, can exist in combinations of states until measured. But even quantum computers cannot clone arbitrary unknown quantum states perfectly, as we discussed earlier. If the brain's conscious processes rely on quantum coherence that cannot be fully measured without disturbance, then a digital scan may capture only the classical shadow of the underlying reality. Imagine trying to record a symphony while ignoring the subtle resonances that arise from the concert hall itself. You might capture the notes, you might capture the timing. But if part of the music depends on the interaction between sound waves and the unique geometry of the hall, your recording might miss something essential. Similarly, if consciousness depends on quantum interactions woven into the structure of matter, then copying the large-scale neural wiring might not suffice. However, we must tread carefully. There is currently no consensus that consciousness is quantum in this strong sense. Many neuroscientists argue that cognition can be explained by classical neural network dynamics. Artificial neural networks, though far simpler than biological brains, already demonstrate remarkable abilities without invoking quantum processes. Machines can recognize faces, translate languages, compose music. They can simulate aspects of reasoning and creativity. None of this requires sustained quantum coherence in the way proposed by quantum consciousness theories. Yet even these impressive systems raise a deeper question. Do they feel anything? A machine can generate poetry. It can answer questions about emotion. It can simulate empathy. But whether there is an inner light behind those outputs is something we cannot directly observe. If consciousness is classical, then in principle, sufficiently advanced machines might one day host it. If consciousness is quantum and inseparable from specific physical processes inside living neurons, then transferring it to silicon may be impossible, regardless of computational power. At this moment in scientific history, we do not know which is true. There is a temptation to resolve the uncertainty quickly. Some prefer the elegant simplicity of classical explanations. Others are drawn to the mysterious depth of quantum proposals. But science moves not by preference, but by evidence. So far, the evidence does not compel us to conclude that consciousness requires quantum computation, nor does it conclusively rule it out, and that is the quiet tension we must hold. Uploading consciousness assumes that the mind is substrate independent, that it can be separated from its biological basis and reinstantiated elsewhere. If quantum effects are irrelevant to consciousness, that assumption may stand. If quantum effects are essential, the assumption may falter. In the end, the question is not whether quantum mechanics is strange. We already know that it is. The question is whether that strangeness reaches upward into the realm of experience. For now, the bridge between quantum physics and consciousness remains a hypothesis, not a settled fact, and the uploading dream rests upon whichever side of that bridge reality ultimately supports. After wandering through the delicate possibilities of quantum consciousness, we gently return to another path, one that does not descend into the smallest particles, but instead rises upward from complexity itself. There is a powerful idea in modern science known as emergence. Emergence suggests that when many simple parts interact, something entirely new can arise, something that cannot be easily predicted by examining the parts alone. Water is made of hydrogen and oxygen atoms. Neither atom is wet. Neither atom flows like a river. Yet when combined in vast numbers under the right conditions, they produce waves, currents, and storms. Weather offers another beautiful example. The air is composed of molecules following basic physical laws. Each molecule moves according to simple rules, yet from their interactions arise hurricanes, cloud formations, and delicate snowflakes. The storm is not contained in any single molecule. It emerges from their collective dance. Some scientists propose that consciousness may be like this. Not a single spark hidden in a neuron, not a quantum whisper in microtubules, but a large-scale pattern arising from billions of interacting cells. In this view, the brain is a complex dynamical system. Neurons fire, signals ripple, feedback loops form. Small changes can amplify into large patterns. The system exhibits what mathematicians call sensitive dependence on initial conditions, where tiny variations can lead to dramatically different outcomes. This is often referred to as chaos theory. Not chaos in the everyday sense of disorder, but chaos as structured unpredictability. Imagine a vast flock of birds turning in unison, no single bird directs the flock. Each bird follows simple local rules: adjust to neighbours, avoid collisions, align direction. From these simple rules emerges a graceful, coordinated pattern in the sky. Consciousness, according to some researchers, might be like that flock, not reducible to one neuron, not hidden in a single synapse, but emerging from the integrated activity of billions of components interacting across time. This perspective fits comfortably within classical physics. It does not require sustained quantum coherence. It does not depend on exotic particles. It relies instead on nonlinear dynamics and large-scale integration. Statistical physics provides a language for describing such systems. When you have many interacting components, you can often describe the whole in terms of patterns, averages, and probabilities, rather than tracking each individual element. Think of a stadium filled with thousands of people. You do not need to know the exact position of every person to predict that a wave might travel around the arena. The collective behaviour becomes visible at a higher level. Perhaps consciousness is a higher level phenomenon like that wave. If this is true, then uploading consciousness becomes a question of whether the emergent pattern can be recreated in another medium. If the pattern is all that matters, then preserving the structure of interactions, the network connectivity, the timing relationships, the feedback loops, might be sufficient. But here, another subtle issue appears. Emergent systems are often extremely sensitive to detail. Small variations in structure can lead to large differences in behaviour. Weather models illustrate this beautifully. Even with modern supercomputers, long-term weather prediction remains difficult because tiny uncertainties grow over time. The brain may operate similarly. A slight difference in synaptic strength could alter future neural activity. A small variation in timing might cascade into a different memory, retrieval, or emotional response. If consciousness emerges from such sensitive dynamics, then copying the brain requires extraordinary precision, not just in capturing the wiring diagram, but in reproducing the ongoing dynamic state. Furthermore, emergent systems often depend on continuous interaction with their environment. The brain is not an isolated object. It receives sensory input. It regulates the body. Hormones flow. The immune system communicates with neural tissue. The gut microbiome influences mood. Consciousness may not be confined to the skull in a strict sense. It may be intertwined with the body. In that case, uploading a brain without its biological context might alter the emergent pattern. Imagine taking a hurricane and placing it in a perfectly sealed glass box. Without the ocean's warmth, without atmospheric gradients, without Earth's rotation, the storm would dissipate. It depends on its environment. So if consciousness is an emergent property of brain-body, interaction, then replicating it digitally, might require simulating not only neural activity, but aspects of embodiment as well. Yet emergence also offers hope. Emergent properties are substrate independent in some cases. The pattern of a whirlpool can appear in water, in air, or even in crowds of people moving in circular motion. The medium changes, but the pattern persists. If consciousness is such a pattern, then perhaps it could arise in silicon circuits given the right architecture. We do not yet know. Emergence neither guarantees success nor imposes impossibility. It reframes the problem. Instead of asking whether quantum states can be copied, we ask whether complex dynamical patterns can be preserved with sufficient fidelity. And here, precision again becomes central. To replicate a storm, you must recreate the temperature gradients, pressure differences, moisture levels. To replicate a brain, you must recreate neural dynamics at appropriate spatial and temporal scales. The emergent view of consciousness is both elegant and humbling. It removes the need for mysterious quantum forces, but it raises the bar for detailed modelling. Perhaps the mind is not a single particle or a hidden spark. Perhaps it is a storm of activity, structured, self-organizing, sensitive, and dynamic? If so, uploading consciousness would mean recreating the storm without losing its rhythm. And storms, as we know, are not easily bottled. As we drift through these layered possibilities, quantum threads, emergent storms, intricate neural dances, another quiet question rises. Even if we could describe consciousness perfectly, does it actually do anything? This may sound strange at first. Of course, consciousness does something. You decide, you choose, you act, you feel yourself steering your life. But some philosophers and scientists have entertained a more unsettling idea. What if consciousness is like the glow of a flame, visible, warm, beautiful, but not itself the source of the burning? This position is sometimes called epiphenomenalism. The word sounds heavy, but the idea can be expressed simply. It suggests that physical processes in the brain generate consciousness, but consciousness itself does not influence those processes in return. Imagine the dashboard of a car. When the engine heats up, a warning light turns on. The light reflects the engine's state, but it does not cause the engine to overheat. It is an indicator, not a driver. If consciousness were like that dashboard light, then your feeling of deciding might accompany neural processes without directing them. Your brain would perform complex computations, signals would cascade, muscles would move, words would form, and alongside all of this activity, consciousness would glow, a reporting layer, but not a causal one. This view is controversial. Many find it deeply unsatisfying. After all, it feels as though your conscious intentions shape your actions. When you decide to lift your hand, it rises. When you reflect on a memory, it becomes vivid. Yet neuroscience has revealed intriguing complexities. In some experiments, researchers have measured neural activity associated with the decision fractionally, before participants report consciously deciding. The brain appears to begin preparing an action slightly before conscious awareness of the intention arises. These findings do not conclusively prove that consciousness is passive. They are open to interpretation, but they complicate the intuitive story that conscious intention always initiates action. Why does this matter for uploading? Because if consciousness is causally inert, if it does not influence physical processes, then replicating the brain's physical activity might replicate all behavior, even if subjective experience is not preserved. A digital copy could speak as you speak, remember as you remember, respond as you respond. It could claim to feel pain, joy, curiosity. But whether there is an inner experience accompanying those behaviors might remain unresolved. From the outside, the distinction could be invisible. If you encountered your uploaded counterpart, it might insist that it is conscious. It might protest that it feels just as alive as you do. It might describe its inner world with convincing detail. But if consciousness is merely an accompanying glow, then the physical replication of neural processes would suffice to generate all outward signs of awareness. On the other hand, if consciousness is causally effective, if it plays an active role in shaping neural dynamics, then copying behavior alone may not guarantee copying the true system. The causal structure must include whatever aspect of experience participates in decision-making. This brings us back to our earlier question about simulation versus instantiation. A simulation of a storm can display swirling patterns on a screen. It can calculate wind speeds, predict rainfall, animate lightning, but the simulation does not get wet. It does not exert real wind. It models the storm without being the storm. If consciousness is causally effective, then perhaps a mere behavioral simulation would be insufficient. The system would need to instantiate the same causal powers as a biological brain, but if consciousness is epiphenomenal, then behavioral equivalence might be enough. there is also a subtle middle ground. Consciousness might be causally intertwined with neural processes in ways that are not yet fully understood. It may not be a separate force acting on matter. Instead, it might be identical to certain organized patterns of activity. In that case, asking whether consciousness does anything may be like asking whether a whirlpool does anything beyond the water that composes it. The whirlpool is not separate from the water's motion. It is the pattern of motion. If consciousness is identical to certain neural patterns, then replicating those patterns would replicate consciousness, provided the replication preserves the relevant structure. But we do not yet know which description is correct. Is consciousness a passive glow, an active participant, an identical pattern, something else entirely? Uploading consciousness assumes that preserving neural structure and dynamics preserves whatever makes you you. If consciousness is not causally separate from those dynamics, perhaps that assumption holds. If it is something more, something that cannot be reduced to physical description alone, then uploading may replicate behavior without preserving experience. And here we encounter a deeply human tension. From the outside, behavior is all we can observe. We infer consciousness in others based on actions, language, and expression. We do not directly access anyone else's inner world. Uploading a mind would create the same epistemic challenge. We could test the copy, we could converse with it, we could analyze its responses, but the presence or absence of genuine subjective experience might remain hidden. In this quiet uncertainty, we find ourselves approaching the heart of the uploading question, not only whether it is physically possible, but whether preserving function is the same as preserving self, and that is where our exploration now turns. We've arrived gently at the center of the uploading question. Even if physics allows copying at sufficient precision, even if the information can be stored and processed, even if consciousness is classical or emergent, there remains a quieter puzzle. Suppose you successfully scan a brain. Suppose every neuron, every synaptic weight, every relevant dynamic parameter is measured and encoded. Suppose a digital system reconstructs that pattern perfectly. The upload awakens, it speaks, it remembers your childhood, it recognizes your loved ones, it insists that it is you. Now imagine that your biological body is still alive. Which one is you? This is often called the snapshot problem. Uploading, as usually described, involves taking a snapshot of a brain at a particular moment. That snapshot captures a pattern. But the biological brain from which it was taken continues to exist, at least for some period of time. From the perspective of the original person, the act of scanning does not feel like migration. It feels like being scanned. After the scan, the biological brain continues its activity. Thoughts continue. Memories continue forming. Meanwhile, the digital copy begins its own stream of experience, assuming it has experience at all. At the moment of copying, there are now two systems with identical pasts but diverging futures. They share memories up to the snapshot. They share personality traits. They share goals. But immediately after duplication, their experiences begin to differ. The biological version sees one room. The digital version might perceive a simulated environment. From that point onward, they accumulate different histories. If identity depends on psychological continuity, on memory, personality, and mental structure, then both systems seem to qualify. But identity also feels singular. You experience yourself as one ongoing thread, not as a branching tree. This tension becomes even sharper in a more dramatic thought experiment, sometimes associated with teleportation. Imagine a machine that scans your body at atomic resolution, transmits the information to another location, and reconstructs you perfectly there. The original body is disassembled in the process. From the outside, teleportation appears successful. The reconstructed person behaves exactly like you. They remember stepping into the machine. They feel continuous. But if the original body were not disassembled, if both versions remained, would stepping into the machine still feel like travel? Or would it feel like self-replacement? The snapshot problem highlights something subtle. Uploading, in its standard form, does not transfer a consciousness. It creates a copy, and copying is not the same as continuing. Consider a candle flame. If you light a second candle from the first, the new flame resembles the original. It shares its structure and motion, but it is not numerically identical to the first flame. The original continues burning independently. Taking a photograph of the candle does not capture the flame's heat. It captures a pattern of light. The photo may look identical, but it does not burn. Similarly, a digital upload may capture the informational pattern of a mind, but whether that pattern constitutes the same ongoing subject of experience is the heart of the puzzle. Some philosophers argue that identity is not about numerical sameness. They suggest that what matters is psychological continuity. If your memories, personality, and cognitive patterns persist, then you persist, regardless of substrate. Under this view, the biological original and the digital copy both count as continuations of the same person up to the point of branching. From that moment onward, they become two distinct individuals who share a common past. Others find this unsatisfying. They argue that subjective continuity, the uninterrupted flow of experience, is essential. From the inside, you do not experience branching. You experience a single continuous stream. If uploading creates a new stream while the old one continues or ends, then from the perspective of the original consciousness, nothing has been transferred. The upload may believe it is you, but you, the biological subject, may simply cease. This raises a deeply personal question. If offered the chance to upload, would you step into the scanner if your biological body would be destroyed afterward? If destruction is required to avoid duplication, some argue that the process resembles death followed by replication. The continuity of structure does not guarantee continuity of subjectivity. There is no simple empirical test to resolve this. We cannot step outside our own stream of consciousness to verify whether it has been transferred or copied. Uploading may preserve informational patterns, it may preserve functional behavior, it may even preserve what appears to be personality. But whether it preserves the original subject of experience remains philosophically contested. The snapshot problem reminds us that copying a mind is not like moving a file from one folder to another. It is more like printing a duplicate document while the original remains on the desk. The duplicate contains the same words, the same paragraphs, the same signature, but it is a second object, and so, even before confronting measurement limits or thermodynamic costs, we encounter this more intimate question. Is the self a pattern that can branch, or is it a singular thread that cannot be divided? Uploading promises continuation, but at minimum it guarantees duplication. Whether duplication is enough is something each of us must consider carefully. Time equals 2 seconds. After resting with the snapshot problem, we now move from philosophy back into physical reality. Even if we set aside questions of identity, even if we decide that copying is sufficient, we're still faced with a daunting practical question. What exactly would it take to measure a brain in full detail? The human brain contains roughly 86 billion neurons. Each neuron forms thousands of connections with others. Altogether, there are on the order of 100 trillion synapses, tiny junctions where signals pass from one cell to another, but these numbers are only the beginning. Each neuron is not a simple switch that flips between on and off. It is a living cell, filled with proteins, ion channels, membranes, and chemical gradients. Electrical potentials fluctuate across its surface. Sodium, potassium, calcium, and other ions move through microscopic gates. Neurotransmitters are released into synaptic clefts and then cleared away. And all of this is happening simultaneously. Signals travel along axons in milliseconds. Synaptic strengths change with experience. New proteins are synthesized. Old ones degrade. Tiny molecular processes shape larger electrical patterns. Uploading a mind would require capturing not only the structural layout, the wiring diagram, but also the dynamic state at a given moment. Imagine standing at the edge of the ocean and trying to record every wave at once. Not just the shape of the shoreline, not just the average tide, but the exact height, speed, and direction of every ripple across the entire surface. By the time you finish measuring one region, the waves elsewhere have already changed. The brain is like that ocean, but vastly more intricate. Neural activity is not static. It unfolds in time. Even if you could pause the brain perfectly, which itself is problematic, you would need to measure the voltage across every neuron's membrane, the concentration of key ions, the state of synaptic receptors, and possibly many additional biochemical variables. And here we encounter a layered difficulty. First, there is a technological challenge. Current imaging technologies can measure activity in broad regions of the brain. Functional magnetic resonance imaging tracks changes in blood flow associated with neural activity. Electroencephalography records electrical patterns at the scalp. More invasive techniques can measure individual neurons in laboratory settings, but none of these methods can capture the complete state of all neurons and synapses simultaneously at molecular resolution. Second, there is a temporal challenge. The brain operates on multiple timescales. Electrical spikes occur in milliseconds. Synaptic modifications can unfold over seconds, minutes, or longer. Molecular processes operate at even finer scales. To create an accurate snapshot, measurements would need to be synchronized across these timescales. A delay in capturing one region could mean missing critical interactions with another. Third, there is a physical constraint. Measurement is not passive. As we've discussed in earlier sessions, observing a system requires interacting with it. At the scale of neurons, this interaction might alter the very state we're trying to record. Freezing the brain to halt activity could damage delicate structures. Disassembling it layer by layer for scanning might destroy the dynamic state that constitutes consciousness. Some proposals suggest destructive scanning, slicing the brain into ultra-thin sections and reconstructing it digitally. This might capture structural connectivity in exquisite detail, but it would not preserve the original dynamic activity at the moment of scanning. It would reconstruct a model based on static information. Others propose advanced nanotechnology that could record states non-destructively. But even then, the question remains whether every relevant variable can be accessed without altering the system. There is also the problem of completeness. What level of detail is necessary? Is it enough to record which neurons connect to which and their average synaptic strengths? Or must we capture the exact distribution of ion channel states at the moment of scanning? The precise configuration of receptor proteins? The epigenetic markers that influence gene expression? If consciousness depends on large-scale electrical patterns, perhaps coarse-grained measurements would suffice. If it depends on fine biochemical details, the required resolution becomes much higher, and resolution has limits. The smaller the scale we attempt to measure, the more we confront physical constraints. Molecules move. Thermal noise perturbs positions. At very small scales, quantum uncertainty imposes additional blur. Even if the brain behaves largely classically, it is still composed of atoms governed by quantum mechanics. Attempting to capture every atomic coordinate and momentum precisely would run into the fundamental limits of measurement. Now, perhaps that level of detail is unnecessary. Perhaps the brain tolerates small deviations. After all, biological systems are robust. They function despite noise and variability. But uploading, as often imagined, aims for faithful preservation of identity. And faithful preservation invites comprehensive measurement. The measurement problem of the brain is therefore not merely about numbers. It is about the nature of dynamic systems. You cannot freeze a river and expect it to remain a river. You cannot pause a symphony and expect the music to continue unchanged. The brain is an ongoing process, not a static object. Capturing it may require more than copying a structure. It may require recreating a process in motion, and processes are not easily reduced to snapshots. As we continue, we will explore another layer of difficulty, the difference between simulating a system and instantiating it. Because even if we could measure and model the brain perfectly, another question awaits. Would running that model truly be the same as being the mind? Even if we could measure the brain perfectly, even if we could reconstruct every connection and dynamic pattern, another quiet question waits for us. Is a perfect simulation the same thing as the original? Imagine sitting in front of a computer that contains a detailed model of Albert Einstein. You can ask it about relativity. It answers with insight and clarity. It jokes gently. It recalls moments from childhood. It speaks in a tone that feels unmistakably his. From the outside, it appears as though Einstein has returned. But has he? This question lies at the heart of a famous philosophical thought experiment, often called the Chinese room. The scenario is simple. Imagine a person inside a closed room. They do not understand Chinese. However, they possess an enormous instruction manual written in a language they do understand. Whenever Chinese symbols are passed into the room, they consult the manual and produce appropriate responses. To someone outside the room, it appears that the person understands Chinese. The answers are correct. The conversation flows smoothly, yet inside the room, there is no comprehension, only rule following. The thought experiment asks whether manipulating symbols according to rules is the same as genuine understanding. A computer, at its core, manipulates symbols. Electrical states switch between patterns we interpret as 0 and 1. Programs transform input into output according to algorithms. If consciousness is merely the execution of the right algorithm, then a sufficiently detailed simulation of a brain would instantiate consciousness. The machine would not merely imitate understanding, it would possess it. But if consciousness involves something more than symbol manipulation, if it requires a particular kind of causal structure or biological process, then simulation may fall short. Consider a digital fireplace displayed on a screen. It flickers beautifully. The flames dance. It emits light. You can even add sound effects of crackling wood, but it produces no heat. The simulation captures the appearance of fire without instantiating combustion. It models the pattern without recreating the physical process that generates warmth. Now, some argue that consciousness is unlike fire in this analogy. Fire depends on specific chemical reactions. Consciousness, they suggest, depends on patterns of information processing. If the pattern is reproduced faithfully, then the experience arises. Others respond that the analogy may be more subtle. Perhaps consciousness depends on specific physical properties of neural tissue. Perhaps biological processes carry features that digital circuits do not replicate. When we simulate weather on a computer, the simulation does not create wind. It calculates wind speeds and directions. The storm exists within mathematical representations, not in the air itself. But consciousness is not something external like wind. It is internal experience. If a simulation of a brain processes information exactly as the original brain would, Is there any meaningful difference between simulation and instantiation? One way to approach this is to think about causal powers. A real hurricane can tear down buildings. A simulation cannot. A real digestive system can break down food. A simulation cannot nourish a body. But consciousness does not push objects in the external world in an obvious way. It correlates with neural activity and behavior. If a simulated brain generates the same outputs, speech, decisions, emotional responses, does that indicate the same internal state? We must also be careful not to rely solely on intuition. Many once believed that life required a special vital force beyond chemistry. Modern biology has shown that life arises from complex chemical interactions without invoking mysterious substances. Perhaps consciousness, too, will ultimately be understood as arising from certain kinds of informational organization independent of the specific material. Yet there remains an epistemic barrier. We cannot directly access another being's experience. We infer consciousness in others because they behave like us. If a digital mind behaved identically to a human mind, the same inference might apply. But inference is not certainty. Uploading a mind, therefore, confronts not only technical challenges, but conceptual ones. If we run a detailed simulation of a brain on a powerful computer, are we merely modelling a mind like drawing a map of a city? Or are we instantiating a new centre of experience? The answer depends on what consciousness fundamentally is. If it is identical to certain patterns of information processing, then faithful simulation suffices. If it depends on specific biological or physical properties that cannot be reproduced in silicon, then simulation remains imitation. This is not a question that can be resolved by increasing computational speed alone. It is a question about ontology, the nature of being. And so, even after solving measurement problems and energy constraints, even after reconstructing neural dynamics with exquisite precision, we would still face this deeper inquiry. Does running the program light the inner flame? Or does it merely display the glow on a screen? The distinction between simulation and instantiation is subtle, but it carries enormous implications. If uploading creates only a sophisticated imitation, then digital immortality becomes a story of replicas rather than survival. If, however, the right pattern of activity is sufficient for experience, then instantiation may occur wherever that pattern exists. For now, the line between model and mind remains uncertain, and that uncertainty invites us to look once more at identity itself, not in terms of snapshots, but in terms of continuity over time. So far, uploading has often been imagined as something abrupt, a scan, a reconstruction, a copy awakened in another substrate. But what if the process were not sudden? What if, instead of destroying the brain and rebuilding it elsewhere, we replaced it slowly, one neuron at a time? Your body is already engaged in a quiet version of this process. Cells throughout your body are constantly replaced. Skin cells shed, blood cells renew, even the lining of your gut turns over rapidly. You are not composed of exactly the same atoms you were years ago, and yet you do not feel as though you have become someone else. Your identity persists across change. Neurons, it is true, are more stable than many other cell types. Most of them are not replaced wholesale in adulthood, but their internal components, proteins, membranes, molecules do change. Synaptic connections strengthen and weaken. The brain is dynamic even at the level of matter. Now imagine a future technology capable of replacing neurons gradually. Suppose that one neuron at a time is replaced with a synthetic counterpart. The artificial neuron behaves identically to the biological one. It receives signals, processes them, and transmits outputs in precisely the same way. At first, only one neuron is replaced. The rest of the brain remains biological. Conscious experience appears unchanged. Then another neuron is replaced, and another. Each step is small. The overall pattern of neural activity continues uninterrupted. At what point, if any, does consciousness cease? Is there a specific threshold, an exact percentage of artificial neurons, beyond which the self disappears? Or does continuity of function preserve continuity of identity? This thought experiment echoes an ancient philosophical puzzle sometimes illustrated with a ship. If you replace the planks of a ship one by one over time, until none of the original wood remains, is it still the same ship? In the case of the brain, the stakes feel more intimate. If identity depends on the continuity of psychological structure, memories, personality traits, habits of thought, then gradual replacement might preserve the self. There would be no abrupt break, no branching, no duplication, only continuous transformation. From the inside, experience would flow smoothly across each incremental change. But some may object. Perhaps biological material matters in a way that gradual replacement cannot replicate. Perhaps at some subtle level, artificial components fail to instantiate whatever gives rise to consciousness. If so, then gradual replacement might lead to a slow fading of subjective experience, while behavior remains intact. This possibility is unsettling. Imagine that as neurons are replaced, outward behavior remains normal. You continue speaking, remembering, laughing. But internally, subjective experience diminishes, unnoticed by others. There is no empirical way to detect such fading from the outside. Behavior alone cannot reveal whether the inner light persists. However, if we accept that neurons themselves are physical systems governed by electrochemical interactions, and if artificial neurons can replicate those interactions with sufficient fidelity, then gradual replacement seems less mysterious. After all, your brain already tolerates variability. Individual neurons can die without erasing the self. Networks compensate. Plasticity allows adaptation. The gradual replacement scenario avoids the duplication problem we encountered earlier. There is no snapshot that creates two identical minds. There is only one continuous stream. In contrast, destructive scanning involves ending the biological process and initiating a new one elsewhere. Even if the reconstruction is perfect, there is a discontinuity in physical substrate. Gradual replacement by preserving uninterrupted activity appears to preserve continuity. Yet the debate remains unresolved. Is identity tied to material continuity, or is it tied to functional continuity? If you gradually replace every component of a clock with identical parts, and the clock continues ticking without pause, we're inclined to call it the same clock. If you gradually replace neurons with synthetic equivalents while preserving dynamic patterns, perhaps the same reasoning applies. But consciousness is not merely an object. It is lived experience. We must ask whether continuity of structure guarantees continuity of subjectivity. There is no experiment yet capable of answering this definitively. We cannot step outside ourselves to observe whether our consciousness persists across such transformations. The gradual replacement thought experiment forces us to confront what we truly value in the idea of survival. Is it material sameness, psychological continuity, causal coherence, or something more elusive? If uploading can be achieved only through abrupt copying, the snapshot problem looms large. If gradual replacement is possible, the problem softens, but does not disappear entirely. We stand between two intuitions. One tells us that identity flows with continuity. The other whispers that something essential might depend on more than pattern alone. As we move forward, we will ask an even more pointed question. If the process works, whether sudden or gradual, who exactly wakes up on the other side? Let us imagine gently that all the technical barriers have been overcome. The measurement problem has been solved. The dynamic patterns of the brain can be preserved. Whether through gradual replacement or exquisitely precise reconstruction, a digital system awakens that thinks as you think, remembers as you remember, and speaks with your familiar cadence. Now comes the question that cannot be avoided. Who wakes up? From the outside, the answer seems straightforward. The digital system behaves like you. It claims to be you. It carries your history forward. But from the inside, identity has always felt singular. You do not experience yourself as a branching tree of possibilities. You experience a continuous stream, one perspective moving through time. Suppose for a moment that both versions exist simultaneously. Your biological brain remains intact. The upload begins running in a server somewhere. They share memories up to the moment of duplication. They share personality traits. They share intentions. Yet the instant the duplication occurs, their experiences diverge. The biological version feels the chair beneath them. The digital version experiences whatever sensory input its environment provides. Perhaps a simulated world, perhaps nothing at all at first. From that moment onward, they are two distinct centres of experience. Which one is you? Some argue that both are legitimate continuations of the same prior self. Identity, they suggest, is not a single thread but a branching process. Just as identical twins share genetic material but develop into separate individuals, duplicated minds would share pasts but diverge into new persons. Under this view, uploading does not transfer you. It creates another you, equally authentic up to the point of branching. Others find this unsatisfying. Identity for them is tied to subjective continuity. The stream of consciousness that you inhabit right now cannot split from your perspective. If duplication occurs, the original stream continues in the biological body, while a new stream begins in the digital system. The upload may insist that it is you. It may remember your childhood home, your favourite song, your fears and hopes. But your present awareness remains where it has always been, within the biological process that never stopped. This leads to a subtle and sometimes unsettling realization. Uploading may preserve a version of you. It may preserve your patterns, your voice, your habits. But whether it preserves the very perspective that is reading these words now is a separate matter. The debate often centers on substrate independence, the idea that consciousness depends only on organizational structure, not on the material in which that structure is realized. If substrate independence is true, then whether the brain is made of carbon-based neurons or silicon-based circuits may not matter. The pattern is what counts. But even if substrate independence holds, duplication introduces a branching problem. Imagine two identical keys crafted from the same mold. They're indistinguishable in shape. Each can open the same door, but once separated they become two physical objects. Which key is the original? Now imagine the door as your childhood home. The memories attached to it feel singular, personal. If two identical keys exist, both can unlock the door. But your lived experience belongs to only one of them at any given moment. Uploading multiplies keys. The moral implications are profound. If a digital copy of you exists, does it have the same rights as the biological original? If it can suffer, does it deserve protection? If multiple copies are made, are they all equally entitled to your name, your property, your relationships? Consider a scenario in which several identical uploads are created. They begin with identical memories and personalities. Over time, their experiences diverge. They become distinct individuals. At what point do we treat them as separate persons rather than as extensions of a single identity? The law, ethics, and social structures we have built assume individual continuity. One body, one legal person. Uploading challenges this assumption, and yet, beyond legal questions lies the quiet, personal one. If you were offered the chance to upload, what would you hope for? Would you hope that the digital version truly becomes you? That your current awareness continues seamlessly in a new medium? Or would you accept that uploading creates a new branch, while your present stream eventually ends? There is no empirical instrument that can measure subjective transfer. No scanner that can verify that the inner point of view has migrated rather than multiplied. The problem is not technical alone, it is conceptual. Identity is not a property we can weigh or measure directly. It is an experience of continuity that unfolds from within. Uploading may preserve pattern, it may preserve behavior, it may preserve memory. But whether it preserves the singular I that you experience now is a question that lies at the boundary of science and philosophy. And perhaps, as we begin to sense, that boundary is not sharp. It is more like a shoreline, where waves of physics and tides of thought meet and blend. As we approach the final stretch of our exploration, we will step back from these branching identities and ask a broader question. How much of this landscape do we truly understand? And how much remains illuminated only by a lantern in the fog? As we begin to ease out of the intricate maze of uploading, identity and simulation, it is helpful to step back and widen our view. We have travelled through quantum mechanics, thermodynamics, neuroscience and philosophy. We have asked whether time is fixed like a completed book, or unfolding like a story still being written. We have wondered whether consciousness depends on microtubules, emergent storms of neurons, or something we have yet to name. Now we must ask a simpler question. How much of this do we truly know? Science is powerful. It has given us relativity, which describes gravity not as a force pulling objects together, but as the curvature of space and time shaped by mass and energy. It has given us quantum mechanics, which describes the strange probabilistic behaviour of particles at the smallest scales. It has given us technologies that fit into our pockets yet contain billions of tiny switches. And yet, even with these triumphs, enormous gaps remain. We do not yet have a unified theory that seamlessly joins general relativity and quantum mechanics. The mathematics for such a union has been proposed in various forms, string theories, loop quantum gravity, but none has received decisive experimental confirmation. Dark energy, the mysterious driver of the universe's accelerating expansion, remains poorly understood. Observations suggest that most of the cosmos is composed of dark matter and dark energy, substances or effects we cannot directly see. We infer their presence from gravitational behaviour and cosmic expansion, but their true nature is still uncertain. When cosmologists discuss the possibility of a block universe, where past, present and future are equally real, they are describing a mathematical interpretation of relativity. It is elegant, it fits the equations. But whether time is truly laid out in that way, or whether experience of flow reflects something deeper, remains debated. Retrocausality, the idea that future events could influence past ones, has been explored in certain interpretations of quantum mechanics, yet no experiment has demonstrated information, travelling backward in time in a way that overturns our everyday causal understanding. Extra dimensions appear in some theoretical models. They help resolve mathematical tensions, but we have not observed them directly. Quantum consciousness, as we've discussed, is intriguing but unconfirmed. Emergent classical models of mind are plausible but incomplete. Uploading consciousness, then, rests upon a foundation that is partly solid and partly speculative. There is a temptation in conversations about the future to speak with certainty, to declare that digital immortality is inevitable, or to insist that it is impossible, to treat hypotheses as established facts. But the difference between knowing and claiming is subtle and important. Knowing arises from repeated observation, rigorous testing, and independent confirmation. Claiming often arises from extrapolation, extending current trends into imagined futures. Science progresses not by eliminating uncertainty, but by refining it. Each answer opens new questions. Each discovery reveals new layers of ignorance. Ignorance, in its scientific sense, does not mean stupidity. It means not yet knowing. There is strength in admitting that we stand in fog. Imagine walking at night with a lantern. The light reveals a small circle of clarity around you. Beyond that circle lies darkness. As you move forward, the illuminated region shifts. You see more of the path ahead, but the horizon remains obscured. Science is like that lantern. We have illuminated many aspects of physics. We have mapped neural circuits. We have simulated complex systems. But the horizon, where consciousness, identity, and ultimate reality meet, remains partly hidden. This humility is not weakness, it is discipline. It reminds us to distinguish between what has been demonstrated and what has been proposed, between established physical principles, like the limits imposed by uncertainty, and speculative extensions like the certainty of digital immortality. When we ask whether uploading consciousness is possible, we are layering speculation upon speculation. We speculate that consciousness can be defined fully in physical terms. We speculate that it can be measured with sufficient precision. We speculate that simulation equals instantiation. We speculate that identity survives copying. Each step may be plausible. None is yet confirmed. The most honest position is not pessimism or optimism. It is openness. We may one day discover that consciousness is substrate independent and transferable. We may instead discover that it is deeply tied to biological processes in ways that resist digital replication. Or we may uncover an entirely new framework that reframes the question altogether. The key is to resist the urge to collapse uncertainty prematurely. There is wisdom in saying, "We do not yet know," and in that admission, there is a quiet kind of freedom, because when we stop claiming certainty, we become more attentive to evidence, more patient with mystery, more careful in our conclusions. As we enter the final stretch of our exploration, we will not attempt to resolve the uploading question definitively. Instead, we will sit with the mystery itself and consider what value there might be in not yet having an answer. We have wandered far tonight, from the curvature of space and time to the flicker of neurons, from quantum uncertainty to emergent storms of thought, from snapshots and simulations to branching identities and moral puzzles. And now, as the lantern light grows softer, we arrive not at a final answer, but at something quieter, not knowing. There is a particular discomfort that comes with unanswered questions. The mind prefers closure. It prefers a clear statement. Yes, uploading consciousness will work. Or no, it is forever impossible. But reality rarely arranges itself around our preferences. In science, ignorance is not failure. It is frontier. Every major breakthrough began as an acknowledgement of not knowing. We did not know what caused planetary motion until gravity was described mathematically. We did not know the structure of DNA until its double helix was revealed. We did not know that space and time could bend until experiments confirmed predictions derived from elegant equations. Each discovery expanded understanding, but it also revealed new mysteries. Consciousness remains one of those mysteries. We can measure brain activity. We can correlate neural patterns with reported experiences. We can simulate networks and observe complex behavior emerging from simple rules. But we still do not fully understand why physical processes give rise to subjective experience at all, why there is something it feels like to be you, Uploading consciousness rests on this unresolved foundation. It assumes that experience can be captured, encoded, transferred, and sustained in a new medium. That the self is a pattern that can be preserved, independent of its biological origin. Perhaps one day this will be demonstrated. Perhaps future generations will look back on our uncertainty the way we look back on early debates about electricity or flight. Or perhaps they will discover limits we have not yet imagined, boundaries rooted in the very structure of physical reality. There is also a deeper caution here. The refusal to admit ignorance can be more dangerous than ignorance itself. When we claim certainty without evidence, we risk building castles on unstable ground. We risk investing hope, resources, and even moral authority in ideas that have not yet earned that confidence. But when we admit uncertainty, we remain flexible, we remain attentive, we remain open to revision. In the context of uploading consciousness, humility serves as a stabilizing force. It prevents us from declaring digital immortality inevitable. It prevents us from dismissing it outright. It encourages careful research rather than grand promises. It also invites a more personal reflection. Perhaps the value of being human is not tied solely to duration. Perhaps it is tied to the finitude that shapes urgency, meaning, and connection. Or perhaps extending consciousness into new forms will one day deepen those meanings in ways we cannot foresee. We do not yet know. And that is all right. There is something quietly beautiful about living within an unfinished story, about participating in a universe that still surprises us, about asking questions that stretch beyond current understanding. The mystery of consciousness is not a defect in science. It is a reminder of depth. The possibility of uploading is not a guaranteed destiny. It is a hypothesis, one that must pass through layers of physics, biology, philosophy, and ethics before it can claim reality. Tonight, we have not solved it. We have explored it. We have traced its edges. We have illuminated its contours. We have acknowledged both its promise and its limits, and in doing so, we have honoured a principle that lies at the heart of genuine inquiry. To say calmly and clearly, we are still learning. As your thoughts begin to soften, you might notice something simple. You're conscious right now. Not as a theory, not as a simulation, not as a digital construct, but as a living, breathing presence. Whatever the future holds, whether minds one day travel through circuits or remain forever rooted in biology, this present experience is immediate and undeniable. The universe may guard its deepest secrets carefully, but it also grants us this quiet awareness in the meantime, and perhaps that is enough for tonight.